I start then, and I am going to talk about construction of asymptotically hyperbolic electrically charged Riemannian manifolds with controlled mass. This is quite a large name. I kind of regret a bit the name that I put because it looks quite complicated, but it's not so complicated, okay? And this is a joint work with Armando Cabrera, Carla Sedebaum, and Penelope Garring. Okay, so yeah. So first I'm going to introduce the setting in which we're going to work. And we're considering here time-symmetric initial data sets of the Einstein field equations in a dimension n+2 with an n greater than or equal than 2 and with a non-positive cosmological constant. We're going to be also interested in electrically charged system. Therefore, we're going to be working with an n+1 dimensional Riemannian manifold. This is the initial data set, carrying a smooth electric vector field E. And all the system is going to be subject to the Einstein-Maxwell constraint equations. And in the time-symmetric case, as I say, we're going to work, so the second fundamental form is 0. These are the constraint equations, where the mu is just the energy density of the non-electromagnetic fields. Okay, in our system, where boundary conditions are going to depend on the value of our cosmological constant. So in the case of a null cosmological constant, our manifold is going to be asymptotically flat. And if our cosmological constant is negative, then our manifold is going to be asymptotically hyperbolic with an hyperbolic radius given by this parameter here. And for the people who are not familiarized with asymptotically hyperbolic manifolds, this means that similarly to asymptotically flat, that something here, sorry. Yes, okay. Similar to asymptotically flat, that means that our manifold outside a compact set is diffeomorphic to the hyperbolic space, and the metric can be written as the hyperbolic metric in these coordinates plus a parameter of perturbation that could be controlled. We will be also assuming the dominant energy condition, which in our case looks like this. And we define the total charge of our system to be this quantity of here. So this is the integral over coordinate spheres of the scalar product of the electromagnetic vector field and the unit normal of these spheres. And when this expression, this omega n, is just the area of the unit n sphere. In particular, in our case, the total charge is going to be always defined because we consider asymptotically flat or asymptotically hyperbolic manifolds. And with this, we also have decay conditions of the electric vector field. So now that we have our setting, I'm going to explain a bit the motivation that we have. And that comes from the Riemannian Penrose Inequality. Marcus talked a bit about this theorem already, so I'm going to just state it here. And the theorem says that given a three-dimensional complete asymptotically flat manifold with non-negative scalar curvature such that the boundary of this manifold is an order minimizing horizon, then we have the following bond on the ADM mass of this manifold. So in particular, the ADM mass is bigger or equal than this quantity here. Well, this is the area of the horizon. And in particular, we have that we have an inequality, equality here, if and only if the manifold is a Schwarzschild manifold. And this is quite interesting, and this is what we have to want to study a bit. And the question that we ask ourselves then is, okay, what happened then if we have that equality is only if it is a Schwarzschild manifold? Then if we have a manifold that fulfills the dominant energy condition and has a mass that is equal to this parameter of here. So let me write it here, 16 pi, plus some epsilon bigger than 0. So we have a manifold with this mass. And what happens if we consider this epsilon arbitrarily close to 0? So if we send the epsilon really close to 0, is this manifold going to be something close to a Schwarzschild manifold then? And well, the answer to this question is no. Apparently, it is not the case. And the reason why we can say that it is not necessarily something close to a Schwarzschild manifold is because of the following result of Mantoulidis and Schoen. So in 2015, Mantoulidis and Schoen proved the following result that states that given a two-dimensional topological sphere with a matrix such that the scalar curvature of this sphere is positive, this implies that this sphere is going to be a stable sphere, then for any m bigger than this lower bound, and this lower bound is the same lower bound than the lower bound of the Riemannian Penrose inequality, then there exists an asymptotically flat manifold with non-negative scalar curvature such that the boundary of the manifold is isometric to this original sphere that we gave and is minimal. And outside a compact set, this manifold is going to be M Schwarzschild manifold. So basically, they managed to show that they can construct a manifold with a boundary that could be something quite different to a round sphere, so it's not necessarily round, and still the manifold is going to have a mass that is going to be arbitrarily close to the lower bound of the Riemannian Penrose inequality. In particular, this suggests instability of the Riemannian Penrose inequality. And this result originally was the intention that they have with this result was to calculate in an exact way Barnick masses. So with this result, you can also calculate in a Barnick mass when your Barnick data has a mean curvature equal to 0. But we're going to focus here a bit in the suggested instability. Okay, so the way how they show this is, well, they consider then the original sphere, which I draw here a bit curvy because I want to show that it's not necessarily a round thing. And they consider a piece of Schwarzschild. And then what they did is to consider a cylinder, which is going to be a color extension, in which they make this sphere rounder, rounder, and rounder, and rounder, until they get kind of a round sphere. And then they manage to make it rounder, to glue this to this original Schwarzschild manifold. And they did all of this in a smooth way and preserving the positive scalar curvature of this color extension. And in particular, we have that in this new manifold, this is going to be an horizon. That means that the mean curvature is going to be null. Okay, so this results shows in particular that the Riemannian Penrose inequality is apparently non-stable. And as the Riemannian Penrose inequality has also several generalizations, for instance, it has been also proved in the higher dimensional case, and it is also proof for the charge case. In the case in which is a charge, for example, you get just an extra term here, which looks like this. Just write it here just for completeness. So there are already other generalizations of this theorem, and therefore it's also interesting to see generalizations of this construction of Mantoulidis and Schoen. And this has also already been done. So first generalization was studied by Cabrera Miao in 2018, and they proved that the Mantoulidis and Schoen construction also holds for higher dimensions. Then by Cabrera, Sadabon, and McCormick, they study the asymptotically hyperbolic case, and they show also that it holds. So there is also a hyperbolic Penrose-Riemannian inequality, or it is a conjecture actually, and they show that it will be also unstable if it is proven. And then for the electric case, this is they also, well, Alai, Cabrera, and Sadabon show that in this two-dimensional case, and with charge, on small charge, they managed to generalize this Mantoulidis and Schoen construction. It is important to realize that here in the hyperbolic case, we don't talk about a Schwarzschild manifold, we talk about an anti-de Sitter Schwarzschild manifold then. And in the charge case, what we have is that the manifold outside compact set looks like a Reiser-Nostrum manifold. Okay, so these are several generalizations of the Schwarzschild. And what we do then in our joint work is to generalize all the previous results and combine them as well, so that we have this construction for higher dimensions from n greater or equal than 2 for a non-positive cosmological constant, and for a charge as well, with a small charge. Also something I forgot to mention is that in the case of charge, you not only need to glue all these manifolds in a smooth way, you also need to glue the electric vector field of the Reiser-Nostrum manifold in a smooth way with a vector field that we have here. So there is two things to glue in that case. Okay. Now that I'm introduced everything, I'm gonna just state the result then of our theorems or generalization, which is actually quite large. So I had to put it into 2 slides and simplify a couple of things. So let's start with the assumptions of the results. Basically, we say that, okay, given a n-dimensional sphere with n greater or equal than 3, and if the dimension is bigger than 3, we additionally suppose that the sphere has pointwise 1/4 pinched sectional curvatures. That means that at any point, the quotient between the maximum of the sectional curvature and the minimum of the sectional curvature is smaller than 4. And we then so suppose, okay, given a non-negative lambda, which is going to be your cosmological constant, then a q, a real number q, which is going to be your charge, and we say that it's going to be small, and the smallness is going to be determined by the initial geometry of this sphere. And then we also need to suppose then that the following function, this quite big function of here, admits a positive zero in which the derivative of this function is positive. So what is this function of here? This function of here is the generalization of the Reiser-Nordström parameter. So this is the parameter that appears in a Reiser-Nordström manifold in the case in which we have a cosmological constant and we are in higher dimensions. So in particular, if we set n equal to 2 here and lambda equal to 0, this will be the parameter of the Reiser-Nordström manifold. And if we just set the q equal to 0, this is just going to be here, the parameter that we find in the metric of a Schwarzschild manifold. And this condition of requiring that this function has a 0 and this is a derivative here is to make sure that we have an horizon, an horizon in this manifold, and that our Reiser-Nordström manifold is substremal. Okay, so this is important for construction. Without this, the construction doesn't work. And in this function of here, what we have as a mass is this parameter of here, which is also quite a big parameter. And what is this parameter of here? Well, this parameter is the generalization of what we saw on the right-hand side of the Riemannian Penrose inequality. So if we set the lambda equal to 0 and the q equal to 0 and n equal to 2, this piece of here will be the right-hand side of the Riemannian Penrose inequality. And if we introduce the q again, that will be the right-hand side of this Riemannian Penrose inequality with charge that I just wrote there. Okay, so these are the assumptions. These parameters, this function has a 0, and if we have higher dimensions than 3, then we need this assumption on the sectional curvatures of the sphere. Then given this, we have that for any n bigger than this parameter of before, we have that there exists a geodesically complete n+1 manifold which satisfies the dominant energy condition such that the boundary of this manifold is minimal and is isometric to the initial sphere that we gave. Outside compact set or manifold coincides with a anti-de Sitter Reiser-Nordström manifold with cosmological constant lambda and charge q. And E, which is the electric vector field, eventually coincides with the electric vector field of this Reiser-Nordström manifold that we have. So in particular, this theorem, what it's proving is that any of these possible generalizations of a Riemannian Penrose inequality will be also unstable, just as was shown in the two-dimensional case. Okay, and this paper is going to be soon in archive, and that's everything that I wanted to say. So thank you for your attention.
Many thanks for your talk. Is there any questions or comments about the result of Alejandro?
So I'm trying to understand this assumption outside a compact set M coincide with the spatial lambda Reiser-Nordström manifold. So,
yes,
but this M is a hypersurface in space-time, yes?
Yes, it's gonna be. This is an initial data set.
You assume that your slice outside the compact region is fixed, yes? you don't admit that maybe in this space-time you can choose another slice, you know, just
No, we're working just with an initial data set. Yes, we're not considering
yeah,
here
but
the space.
if you look only on initial data set, you should be more careful because, for instance, if you start with the usual Schwarzschild and you are only interested internally on a free slice, then there are flat slices. You know, just in Schwarzschild you have just flat slice. The Riemannian metric is just the Euclidean metric. The ADM mass is 0, and you meet some problems. Of course, if you look carefully, what is the extrinsic curvature of this slice, you meet some problems with this extrinsic curvature. But this is extra data which you are not interested in. You know, just
yes.
So this is my comment that what is the real assumption?
No, the stretching curvature is going to be null. It's going to be 0. We consider time symmetric initial data sets. And this is, you could think about this as a poorly Riemannian on the Riemannian result. So actually this is just to show instability of this Riemannian Penrose inequality. So we really don't talk about here about the space-time. This is just saying that it's showing the instability of these manifolds that get close to the optimal value.
Okay, so from the beginning to the end, you have time symmetric data, yes?
Yes, all the time.
Yeah.
Okay. Asymmetric. Extrinsic curvature is going to be 0.
Okay.
We have a question amongst the participants. Leonardo Garcia Eveling, if I'm.
Yes.
Can you speak?
Can you hear me?
Yes.
Yes, we can hear you.
Yeah. Okay. Thanks. Yeah, my question is, when you talk about the instability of the Penrose inequality, so you say that when you had the parameter epsilon in, I think, a few slides back, so you say when that is very small, the manifold still doesn't need to be close to Schwarzschild?
Yes, and this is a bit one
in the Chrome of Hausdorff, or
that's the thing. That's a bit way heavy, and there's people working this right now, because of course you need to say how close it is. You need to talk about a metric or what distance do you consider, and here we're not talking about that. There are work that has been doing in this direction as well. But what I'm saying but not close is to show that your horizon is going to be not even. It's going to be something quite different to a rotational symmetric. But yes, there have been a work to see this, and apparently, if I'm not wrong, maybe I have some papers here, but apparently it is not going to be stable. But it depends of course, in the distance that you.
Okay, because in the picture where you have this kind of funnel, I imagine it could happen that the volume of the region that you glue maybe becomes very small or something, and then.
No, the construction has the property that the volume is constant. That's something that this construction, I didn't mention that, but this volume of this sphere the whole time here is going to be constant.
Okay, thank you very much.
Yeah.
Any further questions or comments? If no, then many thanks for your talk. Many thanks for the participants. Yes, indeed, we can't do that, unfortunately. And I guess we can make a 5 minutes break, and then Jacek will chair the next session.